Welcome back, everybody. All right, so now we got the integers. So we just built in the previous video this set with operations plus times and an order and two elements that look like the integers, behave like the integers, taste like the integers. For all purposes, those are going to be the integers for us. Now, the next step is the rationals. Okay, so we're going to do a very similar idea. We're going to build the rationals from the integers. And again, we're going to use an equivalence relation. And here's the definition. So now we use a different equivalence relation. This one that we call sim right there. Again, the little tilde. And now we say that AB is equivalent to CD if A times D equals B times C. And again, so what is that we are... So again, we don't have division yet, so this is only what we have in our heads when we are developing this, but so far all we have is addition and multiplication on the integers, and so that's what we are doing, right? So here, we are using multiplication on the integers to define this operation, this equivalence relation, and that's it. We don't have division, we don't even know what dividing means yet in set theory. One thing to comment is here we are using Z plus. So Z plus is the set of all Z that belong to Z, which we have defined so far, such that Z is greater than 0. And of course, greater, I mean greater in the order we defined last time of the natural numbers. And by 0, I mean the 0 of the integers we defined last time. So positive integers, okay? Because the quotients, you might as well take them all to be positive to simplify. And then we take the quotient. The quotient is we take a set of pairs and we say that like two pairs that are equivalent, we want to make them equal. And now we got the rationals. Okay, if you want to do a little picture of what this looks like, let me do it in a second. So here is Z plus C plus for you guys. And now which one is equivalent to which? So for instance, this guy here is 1, 1. It's going to be equivalent to 2, 2 because it's 2 over 2 is 1. 3, 3. These three are all of these are equivalent. So we get that everybody on this line is equivalent to each other. Then, and that's going to correspond in our imagination to the rational 1. The rational one. And then for instance, this one here is 2, 1. It's going to be equivalent to 4, 2. And it's going to be equivalent to 6, 3. And it's going to be everybody on this line. And everybody on this line is going to be equivalent to everybody. Everybody on this line is going to be equivalent. Everybody on this line. This one is 1 minus 1, 2 is going to be equivalent to negative 2, 4 corresponds to that line. So now we still have that. Now our equivalence relations are still things in a line, but then in the previous case we had a bunch of parallel lines. They were all the parallel lines giving us the integers. Now we have, well, first we can use the integers on the first coordinate, so positive and negative, and now we are just considering the angle, and the slope is the rational that we are essentially considering, right? So this one is going to be, well, 2 over 1. Well, it's the inverse of the slope. This one is going to be 1/2, negative 1/2, minus 1, negative 2, and as you go up in a circle like this, and you go all the different slopes, you're getting all the possible rationals that there is in this. So each rational here is a whole equivalence class. So a set that contains all these guys, that's going to be the number 1. A set that contains all these guys, it's going to be the rational number 2. Okay, so an equivalence relation, that's how we got the rationals. We need to define the usual suspects. As you imagine who these guys are going to be, 0 is going to be the pair 0, comma 1. What 0 do we mean? Well, it has to belong to the integers and the 1 of the integers. We could have chosen 0, 2, 0, 3. They are all equivalent to each other, all those pairs. And we take the equivalence class of this guy, right? And then 1, 0, 1, the 1 of the rationals is gonna be, as you expect, the 1 of the integers divided by the 1 of the pair, 1 of the integers. So that's your number 1. Addition. How we define addition? So if you want to figure out what this formula should be, you will use intuition that the pair a comma b represents a over b, and the pair c comma d represents the rational a over d, which we don't have yet, but that's what we want in our minds. So if you add these two, you're going to have to do a common denominator, and then on top you're going to have ad plus bc, right? That's how you add fractions. So then this is going to be represented by the pair ad plus bc comma bd, right? So that's what it is. And again, like in the case whenever we define something in equivalence classes, we need to make sure that they are well defined, so that the definition doesn't depend on which representative you're taking of the equivalence class. So we need to prove the same thing that we did in the case of the integers when we did addition and multiplication, except the formula is going to be a bit more complicated than that one. Well, not that much. You have to show that ad plus bc comma bd is equivalent to a prime d prime plus b prime c prime comma b prime d prime. And again, this definition right here is gonna, no, this lemma right here, I mean, it requires just playing around with what you know and getting what you want. Essentially, that's the same way we did in the previous video. It's just a little bit of a few tricks, but not too hard. I mean, you know it's gonna be true. This is the thing. You have to prove this using the absence of set theory. So then, and what we have so far is that we're assuming we know the properties of the integers, so we can use the properties of the integers to prove this, and that's why it takes a few lines to prove it. But essentially, we know, because we know that this is true from middle school. So we know that's going to be true. So we don't have a doubt that it's going to be true. The only reason you need to prove it is because we need to show that the way we are building this from the axioms and from the integers that we have already, this works, right? So that requires a two-line proof. By the way, again, let's remark that all these operations are addition of the integers, multiplication of the integers, multiplication of the integers. Right? We're using the integer operations to define the rational operations. Cool. Now for multiplication, again, same deal. Exactly the same deal. If you can guess now what you're gonna get. On top of the quotient, you should get a c, and in the bottom, you should get bd of this fraction. So this is what you should be getting. And again, you need to show this is well defined, the same thing as before. And then once you do that, then you have an operation on equivalence classes. And now you have a nice structure, a set of rationals with two operations on them, 0 and a 1. You need the ordering also, which again, you think of the fractions, what this should mean. Do it on a side, a over b less than c over d. That's the same thing as ad less than cd. So that's what it should give you. So then you just pretend you didn't do that, and you just go straight and define this happens if and only if ad is less in the integers cd, because those are integers. Okay, so you define that, and then Right, so if you didn't have the intuition, these definitions are all like super combinatorial and technical, and you're like, okay, I don't know how that works. So then you need to prove it. And what you need to prove is this. You need to prove that the rationals have the property that they should, which is that they are order field. I don't know if you remember from your algebra class, a field is like a ring, but with the advantage that every element has an inverse. Well, except for 0, every other element has an inverse. So arithmetic on these things is much easier. So the same thing: associativity, commutativity, distributivity, inverse, unity, all those properties you need to show. And that is order means that the order behaves well with the operations of addition and multiplication, right? So if you have two things that you add into things, and then you add two things that are bigger, the result is going to be bigger. If you multiply two things that are bigger and positive, your result of the multiplication should be bigger too. That's what order means. Check it out on the textbook. And again, the properties, to prove each of them requires a line or two. So take a look. Try to do a few of them before class, so you can practice how they are. And again, we need to see how the integers fit inside the rationals, because now they are completely different sets, right? These rationals are sets of pairs of integers, and not set of pairs, equivalence classes. Each one contains infinitely many pairs of integers. So they are nothing like integers, but we can embed the integers inside the rationals. And as you can probably guess, if you map z, you're going to map z to z comma 1. Right, the equivalence class of this. Okay, so now we define the natural numbers using the sets. Each number is the set of the previous numbers. We have this embedding of this into the integers, and now we have an embedding of this into the rationals. So we can think of the integers as being inside the rationals and the natural numbers as being inside the rationals, even though formally they are not exactly inside. And of course, once you define embedding, you have to show that the operations and the order that we had on the integers stay preserved. So addition on the integers, if you look at addition of the corresponding rationals, when you go through this map, you should get the same thing. Yeah, it makes sense. That's what you want. So addition is preserved, multiplication is preserved, order is preserved. So these embeddings right here, if you add two things right here, or if you add two things, the images right there, you should get the same thing. That's what it means to be homomorphism. And then once after you have this, now you can say safely that yes, that the integers are essentially a substructure of the rationals that we just defined. Cool. Next steps, the real numbers. See you in the next video.